Okay, so the next concept is that of a monotone function. And in the tradition of mathematics, we're going to introduce a bunch of concepts now, and we're not always going to fully motivate them, but just trust me, it's all going to come together at the end. All right. So first, let alpha and beta be types with partial order less than or equal. So non-strict one. So we'll say that the function f from alpha to beta is monotone if, whenever a is less than or equal to b, then the same is true if you apply f on both sides. All right. So that means f is monotone. It maps smaller elements to smaller elements and bigger elements to bigger elements. But notice that this order is not exactly the same as that one because they work on different types. This is the order on type alpha, and this is the order on type beta. Okay, so I mean the phrase here says they're types with partial order. So each of them has a partial order less than equal. Okay, and you have lots of operators in real life that are monotone, or they preserve monotonicity of their arguments. So I mean, example is cup here, right? So the union, right? So if you make one of the two sides of a union bigger, then the result will get bigger, or stay the same, right? So if you make it bigger or equal, it will get bigger or equal. And you have same with relations, right? If either side of that big circle is made bigger, then the whole relation will only get bigger, will definitely not get smaller. Okay. And the very nice thing about monotone functions, and this is their motivation here, is that they, those from set alpha to set alpha admit least and greatest fixed points. All right. But I mean, this is an example of a non-monotone function. So just to show that not all functions are monotone, you say if f of a is a set. If a is the empty set, you return the univ, and if it's anything else, you return the empty set. So this will keep on swapping. For example, if you start with the empty set, then you get univ, then get the empty set, then you get univ, and we'll just we'll just go like crazy like this. And this is exactly not what monotone is is all about. And you're not going to converge when you're trying to find the least fixed point. This is this or greatest fixed point for that matter. So so this is not nice. And you remember, or immoral or illegal, whichever examples we had before, it was a bit the same flavor, right? It was you're in the predicate if and only if you're not in the predicate. Here we're doing the same thing at the at the level of the fixed point. Okay, so this is the formal definition of monotone. And then we register various operators as monotone. So identity function is monotone. The constant function, the one that ignores its argument, always returns B, is monotone. The union of two monotone functions, f and g, is monotone. The proofs of all these things are pretty monotone. And we have two more operators here. So composition of relations is also monotone, and the restriction operator is monotone. And you see where this is, you see what this is trying to do here. We're building exactly the operators, the properties for the operators that we're going to need later to define the, to define the denotation of the while case. Remember, it relied on these operators. It relied on composition. It relied on union. It relies on restrict, and so on. It relied on identity. So you see, everything will fall into place later. It will not fall into pieces. It will fall into place later.